All right, so again, today marks the halfway transition point between the topics that we've covered up to this point, dealing primarily with your project, and now we're going to get into more data structures and algorithms, algorithm analysis, and the more theoretical things, but it's still going to be a very practical use. So we do that by introducing a very basic data structure that you've been using without really thinking about it up to this point, a list. If you're coming from a Python background, it's built in. That's the basic, you don't even have arrays in Python. The basic collection is going to be a list. Oops, there we go. All right, so, and in Java, we've of course been using lists, array lists, and then we're going to now get into linked lists and different types of lists. But let's have a motivation for why we want to do this. If you're coming from a Python background, you don't know about regular old crappy arrays. If you're coming from a C background, you know the pain that arrays are, right? That you have to dynamically create them in memory. You have to make sure that you pass around the actual size of the array all over the place. You have to make sure that you clean up properly when you're done with the array and that you free up that memory, right? The motivation here is that dynamic data structures are way better than arrays. Even in Java, when you have arrays, you typically don't want to use them, right? Why? Because, of course, you have to create them. So for integer array is equal to new integer of size n, right? Once you've created this, there we go. Once you've created this, it doesn't grow, it doesn't shrink. Right? If I've created this now, an array that holds 10 elements. If I want to now put an 11th element in there, right? I'm out of luck. I'm going to have to recreate a brand new array here. Likewise, if I only take up 5 things, right? Then the rest of this is being wasted, right? If you're going to fill this up with only 5 things, then the rest of it is wasted space. Not only that, but there are gaps, right? What if I enter in something like 42, and 50 over here, and 70 over here, right? Then I've got huge gaps in my array. Why? Because an array is contiguous, right? When it's actually allocated in memory, you've given this chunk of memory where one element is right after the next one, right? It's great for random access, for jumping to a particular element, because all you have to do is calculate the memory offset. If this thing is in memory location XYZ, this one is going to be in memory location XYZ plus 4 times however many bytes it is, right? So arrays are okay if you can't afford anything else. But of course, we can afford dynamic data structures. And we can now leverage the OOP principles that we've talked about, encapsulation, abstraction, and polymorphism, in order to create our own list. Now, of course, remember, you don't actually do this in real life, that if you have a list of integers, right, integer, right, foo is equal to new array list of integers, right? You're good to go. That's what you should be using. But we need to actually understand how this stuff gets implemented and leverage OOP principles in order to understand when to use it and when not to use it. Because when we get over to algorithms and algorithm analysis, you'll see that one very simple operation can take, a couple of seconds or microseconds or whatever using one type of list. But if you simply just change it to another type of list, now it becomes weeks, months, decades, or billions of years to execute. Right? There is a subtle difference. So let's go ahead and get started and understand how the array list is actually implemented by implementing our own array list. I'm going to go ahead and start off, and sorry for the second projector not working today, but at least this one works. Those of you at home, remember that we are on live stream, so here, if you have any questions, go ahead and post to the live stream. Otherwise, at home, you're not going to see that one of the projectors is out. I'm going to go ahead and create a new class here, and I'm going to name it my integer array list. Array list. There we go. All right. And we're going to eventually refine this so that we can generalize it and we can get all the functionality that we want. Okay? So, of course, it's a bad name intentionally, right? As we've already seen, deleting, sorry, here we go, move over here. Arrays are bad. Once created, the size is essentially fixed. You can't grow it, you can't shrink it. You have to do a lot of bookkeeping to keep track of which indices have been used, which ones are free, etc. If you're coming from a C background, then there's even more bookkeeping because you're going to have to pass around everything throughout the entire program. Deleting or removing elements may leave gaps. All right, so the solution here that we're actually going to go with is creating a dynamic list. And what are we going to want? What are we going to want out of this list? We're going to want it to automatically grow, maybe even shrink, right? Without us having to worry about the details, right? That sounds familiar. That sounds like abstraction and encapsulation. That behavior is going to be encapsulated inside of the class, and from outside of the class, it's going to be abstracted away from us. We don't care how it works. We just know that we can use it and get the job done, right? Basic functionality. This is also going to look familiar. We need a way to add things, right? Retrieve things, remove things, and maybe even, change things, or modify. I'll go with modify things. Right? 4 things. Put stuff in, take stuff out, remove stuff, get stuff, modify stuff. Sounds familiar? CRUD, right? Create, retrieve, update, and destroy. Same basic idea of functionality with respect to a data structure as with a database table. You need a way to create stuff, put stuff into the table, retrieve stuff, pull out stuff out of the table, or in this case, the list. Way to update, a way to delete things, okay? So all of those details are going to be encapsulated inside of the data structure itself. We don't want to have to worry about them. But now when we are actually going to write this, this class, now we need to worry about it. But we want to make sure that the outside world doesn't have to worry about these details, right? We want an abstraction, an interface that the outside world can work with that specifies how to use the list, not necessarily how it works, okay? So let me come over here and, I could just, reuse an array list, right? But that kind of defeats the purpose. And why are you writing yet another class to wrap us around another class? So I'm going to write it from the very beginning. We are, in fact, going to have a integer array, right? Okay? We can't get around that. This is an array-based list. And so inside, we are going to keep track of the elements using an array, okay? What should my my integer array list here, what should my constructor look like? So when you create a list, is there anything in that list to start out with? Nope. So I could do something like this. This dot array is equal to new integer of, say, size 0. An array of size 0 is kind of useless. Can you put anything into it? No. So let's think about this in terms of a visualization here. I've not put anything into this array yet. What's its size? Right. So how many things have I put into it? None. So what would you say the size is? If I put things into it, 42, 7, or 3, 7, right? Now there are 3 things in there. How many things are there right now, though? 0. I would say that the size is 0. I could put 10 things into it, right? But that's a different notion of size. That's called, I'll give it a better name there, capacity, right? If you've got a box that can hold 10 books, but there are no books in it right now, then the size of that collection is 0. But its capacity is 10, right? So once we have a different notion of, or separated the notions of oops, I don't want that. Okay, there we go, off that. Once we have a different notion of capacity and size, now we can think about this a little bit differently. I'll go ahead and make the capacity here 10, okay? But what's the actual size? Is equal to 0 initially, okay? That means that we're probably going to want to keep track of that in a variable, private int size. There we go. So that when I create this integer array list, I now have a capacity of 10. I can put 10 things into it without having to worry about running out of room. But initially, it's going to be 0. We, of course, need a way to put things in. Otherwise, we're stuck in the water here, right? So let's go ahead and add a method here to do so. Public void, maybe, add element, right? Int x, okay? An integer x. We're going to add x to the list. So let's go ahead and document that. Adds the given element x to this list. But how? Right? So what would you expect? If this is our list. So think of the list here as an empty list, right? It's not even an array. So it's like a collection, right? There's nothing in it right now, but it is still ordered. So where would you add it to the list? Maybe fast forward a little bit here, and suppose that there's 40, 30, and 20 in the list already. 3 elements of size 3. Now suppose that we want to add 42 into this list. Right? Without any other qualifications, where would you expect it to be added? Would you expect it to be added, say, right here? For some reason, is the second location? Maybe you would expect it to be added to the front of the list. What's a little bit more natural? Okay, let's just go ahead and append it, add it to the end. Right? You can go ahead and rename this add element to end if you want to. You can rename this to append element, right? Et cetera, et cetera. I'm just going to go ahead and make it so that it's add element. And then I'm going to rely on my documentation here to tell you what it's doing to the end of this list, period. There we go. Are we going to tell the outside world, oh, by the way, if it's full, you're out of luck? Then you're going backwards. You're living in a world where you just have arrays. You're living in C world then at that point, right? So how is this going to work? Let me go ahead and try adding it, right? For int I equals 10, I is less than or equal to 100, I plus plus. I know that this is going to work. Or I need actually to create it first, right? My integer array list, I'll call it numbers is equal to new my integer array list. And now I can go with numbers dot add element, and I'll go ahead and add I. So I'm going to add 10, 20, 30, 40, 50, right? How is that going to work? Initially, if you just add 10, where is it going to be added to? Let's look at the picture then. Right? If I add 10 and I'm adding it to the end of the list is of size 0 right now, right? So where would I add 10? To 0. There we go. Now I want to add 20. Where's 20 going to go? Can it go here? Nope. The size is now different. What is the size now after I've added 10? 1. So where is 20 going to go now? Right there. Do you start seeing a pattern? Right? Where are you going to add that element? Right? This dot array dot or something is equal to x. What's that something? 0, 1. This dot size. Right? So if it's 0, it's going to be added to index 0. If there are 5 things in there, where are you going to add it? Right here at the end. 0, 1, 2, 3, 4, 5. All right?
That's what makes zero indexing good for arrays.
Well, 0 indexing is good for arrays generally because, again, it's random access. That you have a certain memory location and then offsets 4 bytes away, 4 bytes away, 4 bytes away. If you start at 0, then it's the math works out. Right.
And it's just an accidental thing that we can exploit for ease.
Well, yes and no. I mean, plus minus 1 is not going to be that big of a deal. Right? Again, we're abstracting away from the outside world. The outside world should not have to worry about that. Right? We should not have to worry about those details. So let's go ahead and run this. Right? Did it work? How am I going to know that it works? Maybe at the end I could print it out. System.out.println numbers. There we go. What would I expect? 10, 20, 30, 40, 50, 60, 70, 80, 100, or 80, 90, 100, right? But I'm getting that thing right there. So suggestions on how to deal with this. I want to print it out, but I want to print it out so that the contents of that list are printed out to the standard output. What is the method that we should be overriding? ToString. So let me come over here and add that. Public string ToString. There we go. And I will go ahead and say string builder, because I'm going to be because I'm going to be appending to it, right? SB is equal to new string builder. There we go. I'll go ahead and initialize it with append with a square bracket right here to begin with, and then at the end I will go ahead and append a closing square bracket. And in between, I will add, or I will concatenate each one of the elements in the array. So help me out with this. For int I equals 0, I is less than this dot array dot length, I plus plus. And what I'll do is sb dot append. Does anybody see any problems with this so far? I, and then, I don't know, concatenate this with a comma right here. And then finally, return sb dot ToString. Let's run this. Looks like it works. Let me go ahead and do, oh, you know what? Plus equals 10 is what I meant to do, so that I'm appending 10, 20, 30, 40, 50. That's what I wanted, sorry. All right, oops. Save. There we go. Should run. Nope. What's wrong? X. I is 10, I is less than or equal to plus. Okay.
Wait, go back, there might be something different.
This dot array is equal to X. I'm giving X. Oh, there. I'm not printing the actual value. What am I doing? I need to go this dot array dot of I. There. I was just printing out the indices. That's why. That was not an intentional mistake. There's definitely intentional bugs in here that we're going to work through, but that wasn't one of them. Ugh. What's wrong? First of all, what am I doing? I'm printing out nulls when I should probably not be, okay? All right, so let's come back over here and rethink this, all right? So add element. Are you just gonna always add it to this dot size? Think about that. Let's go ahead and set a breakpoint here and actually run it. Yeah, switch to the debugging perspective here. All right, so I've got X, which is 10. That's the first element that I'm adding, right? I will go ahead and step over this and look at the array so far. This array. 10 is in there. And then the rest of them are null. Why? Because that's our capacity. We haven't put anything in there yet. All right, go ahead and keep stepping, step. So I'm about to add 20 here. Right? There's X. It is indeed 20. Where am I going to end up adding it? What is the current size?
0.
Still 0. What should I have done here? Once you add something to it, if you're keeping track of the size, what else do you need to keep track of? When you add something, what should happen to this dot size?
Increases.
All right, plus plus. Let's see if that works. 10, 20, 30, 40, 50, 100. Looks good now. All right. Let's come over here and let's print it out on every single iteration to see that each addition actually works. Let me go ahead and run this. Uh-oh. 10, bunch of nulls. Should I be printing these nulls? Are these nulls actually part of the list data structure?
No.
Nope, they are entries in the array, not part of the list. So let me come back over here to my ToString method. Should I be printing out every element in the array? Nope. I should only be printing out what? The first element, the second element, the third element, all the way up to and including the last element, which is kept track of by the size. Keep these two things separate in your mind. A capacity, how much it can actually hold, and a size, how much stuff is actually in there. When I run this, now I see that there's 10, then 20, then 30, then 40, all the way down to 100. Looks good now. Done, ship it. No. I probably want to now add, say, oops, let's go ahead and get rid of that since we know it kind of works. Let's go ahead and add 42 to the end, okay? Is that gonna work? Oops, index 10 out of bounds for length 10. What's happened? We've hit our capacity. If I've added 10 through 100 to an array of size 10, I've filled it up. Where's the next guy going to go? Right? I've filled this up with 10, 20, 30, 90, or 100, I guess, right? Now I want to enter 42. Where's that going to go? We're out of luck now, right? So we need to take care of that eventuality. What should I be doing first before I just put it into the array? Are we at our capacity, right? If the array is full, we need to accommodate, to grow it so we can accommodate the new element. 1M or 2Ms? It thinks it's 2Ms. I do too. Right. So how can we grow an array? You can't, right? That's not how arrays work. Now in C, if you're coming from a C background, malloc, realloc, and calloc, you can realloc, you can try to grow an array, but if you've run out of room, right? If you, or if this memory, this contiguous memory has already been taken, you're out of luck there. So what do we do? We need to make a new deep copy of it, right? So what we'll do is we'll, one, create a new array of a larger size, ... Two, we'll need to make sure to copy over all the old elements from the old array. And then three, update this class's array to point to the new array, the new larger array. Right? This is a deep copy function, right? If you're coming from a C background, then you know how to do this because you've done this now half a dozen times. If you're coming from a Python background, there's this nice deep copy, they call them packages in Python, right? Package, you like import deep copy, and then you can go deep copy dot copy of, or something like that, right? It's built into the language, or it's a standard package, I should say, right? So let's create a new array of a larger size. So I don't know what I should call it. I'll just call it BRR. Why? Because ARR stands for array. What comes next? BRR, right? And a new integer. Should I make it of size 100 or 20 or something like that? Right? Should I hard code that value? Well, what happens when I get to 20, right? Then that's the actual, that's the maximum value that or maximum number of elements that you could ever hold in this class. I'm going to make it as big as the old one, this.array.length, plus, say 10 more. Now you could take a bunch of different strategies here. You could grow this quadratically, right? You could say this times this. So if it was of size 10 before, now it's of size 100. If it was of size 4 before, now it's of size 16. You could double the size, right? I'm just going to go ahead and keep it simple and add 10 to it. That strategy right there would be some question for some empirical analysis, where what's the most efficient way of doing this? And then you'd set up a whole bunch of tests, load tests, and do some empirical analysis, and do a whole millions of runs of this program, sample all of them, and then find out what the best strategy is, okay? But otherwise, it's going to hold now at least 10 more things. We're increasing the capacity. Now let's copy over all those old elements. For int I equals 0, I is less than this.array.length. And I am going to go over the length of the array. I could go over the size, but I'm going to go over the length of this array. I plus plus. Why? Because I know that it's full, right, at this point. Oops, did we even check for that? We didn't write code to do that, did we? So let's write that if statement next. And then move all of this under the if statement. So if this array is full, ... Right? What condition would I check there? How do I know that it's full? How did I know that it was full over here? Once you fill it up with 10 through 100, what's the size of the array at that point? Or what's the size of the list at that point? 10. What was the capacity? 10. So when these two things match, you know that it's full. So let me come over here and say that if this.array.length length is equal to this dot size, then I know that it's full. Okay, yeah.
When you're adding a new element, wouldn't it be, if you're adding a new element to the array, wouldn't it be simpler to just, wait a minute. Never mind, I'll have.
Okay, all right, think about it. Let's copy over all the elements, right? So BRR sub I is equal to ARR sub I. There we go. And then update this class's array to point to the new one. This dot array is equal to BRR. There we go. That line right there is a shallow copy. But remember that we've already made the deep copy by copying everything over, and so therefore this is perfectly fine. Those of you coming from a C background will be cringing right now because, wait, what about the old one? Did we clean up our memory? In C, you'd have to do something like this before, that you'd have to have some sort of a temp variable here, like int star temp is equal to ARR, so that you can go ahead and change that, and then you would go free temp, something like this.
They just have to use a buffer for it.
Something like that, yeah. But do you have to worry about that here in Java? Automated garbage collection. It'll take care of it for you. All right? In fact, there's got to be a better way of doing 1, 2, 3 here. There is. This are arrays dot copy of. Right? Copy of is a deep copy function that you can use. It just takes those 3 steps right there and does it a hell of a lot more efficiently than I did. Right? And what I'm going to do is go this dot array, there we go, and this dot array dot length plus 10. And I'll explain that here in a second. And this dot array is equal to that. Oops. Arrays dot copy of. Right? That's a deep copy function that will copy this array into a brand new array, giving you a brand new array here to put into the old array. This second argument, something like this, and that's going to copy over all those 10 elements. By adding plus 10 here, what it's going to do is it's going to copy over those 10 elements and then pad it out with a bunch of zeros at the end, so that you now have capacity to do the rest of that. Actually, it's a bunch of nulls at the end. Right? You can also truncate it. What if it was -5? Now what that's going to do is that's going to copy the array. If there are 10 elements in it, it's going to only copy the first 5 and make it that new size. Right? I actually want plus 10 here because I want more capacity. Let's see if this works now. Hey, there's 42 at the end. If that Oxford comma there at the end is the coding Oxford comma is bugging you, of course you can go ahead and take care of that by modifying our loop. Okay. In fact, let's do that now. Let's go back over here, and let me go ahead and handle that last iteration of that loop separately, meaning that I'm going to stop short by 1 iteration, come down here, sb.append, this dot array sub. This dot size -1. Why -1?
The size is not 0 there.
It's exactly. If there are 5 elements in there, then where's the last guy? At 5 minus 1, 4. There we go. All right, so let's come back over here and see that, yeah, that looks a little bit prettier. I wonder if that refactoring, that changing, works though. Let's come up here and let's print it out when it's empty. You always need to be thinking about corner cases, edge cases, special cases that don't apply in general. For example, when your list is empty, right? When you want to add something to the end, or when you want to add something to the beginning, or something like that, right? Some edge case there. Let me go ahead and try this and see if it works. Nope. Index -1 out of bounds. Why? When it's empty, what happens to this line down here? Size is going to be 0. Therefore, size -1 is -1. Right? And there, can you print out -1? The thing at -1 index? Nope. So my clever little idea of handling that last iteration separately failed. That's okay. We can still fix it. When you've got an edge case, typically you treat that special. You treat that differently. So if this dot size is equal to 0, in other words, it's empty, then I'll just go ahead and return, empty. Special a special string representation of this. There. Cool. Now when I run this, I get empty and then 10 all the way up to 142. In fact, you could do this as many times as you want. Right. There we go. You can put as many things in there as you want. Why? Because now it's automatically growing. When it gets up to 10 and it's full, it makes it so that it's 20. When it gets up to 20 and it's full, it makes it into size 30, right? Et cetera, et cetera, et cetera. Yeah.
Would would it be a wrong idea to just think of increasing it only by 1?
You could do that.
Because my first question was what would happen with things like later on when we try to implement adding to the specific spot function, they add to something.
We'll take care of that. Yep, we'll take care of that eventually. Right? I'm doing 10 because you don't want to be doing this every single time. Think about what this is doing. Right? Suppose that I wanted to add 1 million elements. So instead of going up by 10 here, I'll go up by ones and then 1, 2, 3. Right? What are you doing every single time if you're only going up by a factor of 1 every single time? Think about when you get up to about, say, 900,000. 900,000, and you just want one more. 900,000, copy all of that, and only increase the size by 1.
Oh.
Right? 900,001 copies. 900,002 copies. Right? This is going to get very, very, very inefficient very, very quickly. In fact, it's still going. Right? Yep.
No.
So let's come back over here and at least kick it down by a factor of 10. This is still going to be very, very inefficient. Right? So maybe you want to kick it up by a factor of 1 million. Should you do that though? That's going overboard. Now I'm potentially wasting a lot of memory, right? Because if you only put 10 things in there, you're wasting about like 4 megabytes of memory or something, right? There's got to be a healthy center somewhere, right? And again, that's going to be some sort of engineering project where you set up a bunch of experiments and find out what works best. In fact, you could probably change this so that it goes up by a factor of 2 each time or something instead. So different strategies. I'm going to keep it simple now because that's not my focus. My focus is on this core functionality. We've got a way to add things. Now let's go ahead and have a way to retrieve things. Right? Public int get element at index. Right? Int index. What this is going to do is we're still going to have 0 indexing. In other words, this is a list. You can go ahead and get the first element at index 0. You can get the 10th element at index 9. Right? I want you to be able to retrieve things, so we'll do it index-based. Returns the element stored at the given index. Code index. Right, there we go. Any other details that we need? Probably not. So, return this dot array at index. Looks safe? Let's find out. So let's come down over here and let's go ahead and say int x is equal to, oh, you know what, I need to kick that down. I don't want to do that. So 10, 20, 30, 40, 50, all the way up to 100. We've added 42 at the end. Let's go ahead and get the element at, get element at index, I don't know, 3. What would you expect? 10, 20, 30, 40, 50, right? So 0, 1, 2, 3. What's there? 10, 20, 30, 40. Right? I'm expecting 40 back. Out.println x. It works. Right? Done? No. Make sure that you're trying to break your code. This is what writing good tests is all about. Not in this section, but another section. Somebody was really clever, and they thought to go ahead and, when they submitted their test case, they filled it up with a bunch of like emojis and Unicode and stuff like that, trying to break the system. That's called fuzzing, right? You'd give it a bunch of intentionally bad input to try to break it. So let's try to give it some intentionally bad input here. What's an index that I probably should not be asking about?
-1.
Okay. What happens? Index 1 out of bounds. An array index? What are you talking about? What's an array? Right. This is an array, my integer array list. Should I be forced, from the outside world here, should I be forced to think in terms of an array? Probably not. What's another bad value that we could give to this? Potentially bad value. 15, right? How many things are in there right now? 10 to 100, so 10 things, and then I added 42 at the end. There are 11 things in there. 15. Oops. So now I'm getting something completely different here. What it's saying is, okay, well, that thing exists, but remember, what is it? It's null. Right? So I'm giving it's not a, it's kind of a, yeah, it is a null pointer exception. What are you talking about, right? What's null? 15 here. You shouldn't be giving me a null pointer exception for this. That problem is occurring inside of the class. That problem needs to be handled inside of the class, and then a proper communication be given to whoever's calling this method. So let's come over here and rethink this. What should I be checking for first? If the index is negative, that's certainly bad. Or if the index is greater than what? There are 5 things in there. 0, 1, 2, 3, 4. Those are safe to ask for. But what about this one? Probably not safe to ask for that one. If the index is greater than this dot size, yep, I like that. If you're going to go with size minus 1, if it's, let's see, 0, 1, 2, 3, 4. Should you be asking for something that's of size 5? Nope. So greater than or equal to size. There we go. So if either of those indices are outside the scope of this, then how should we handle this? Return 0? I don't know. How do you know that there was a 0 there, or that it's just returning 0 because you asked for something bad? Can you distinguish between those two cases? Nope. Again, what if I had put 0 in there instead? Numbers.add element, you can certainly put in 0, right? You might get that back. How do you tell the difference? Flag values are probably not good. Right? So how would you handle this? How does the Java list handle this? If you ask for something that doesn't exist, it throws it back in your face, right? Throw a new illegal argument exception, right? Or index out of bounds exception or something like that. Invalid index plus index. There we go. Now we're going to get back a meaningful message that says something about the internal, that doesn't reveal anything about the internal workings of the class itself. Right? Illegal argument. You can't have invalid index 15. Invalid index -1. Right? -1. There we go. Invalid index 10? I don't know. Nope, that's where we're storing 42. 4. What would I expect back if there's 4? 0, 1, 2, 3, 4. 50, right? There we go. Much better. Not only that, but this is a unchecked exception. I'm not making the mistake that they made 25 years and using checked exceptions everywhere, where you're forced to surround everything with a try-catch. An illegal argument exception is good enough. All right, great. How do I know not to ask for the 16th element here? I'm going to be forced, now I am kind of forced to surround this with a try-catch. I'm asking for something that doesn't exist. How do I know that it doesn't exist? So let's give some more information to the outside world so that they can do defensive programming if they want. Right? Public int get size. Right? Does that look familiar? Right? The size of a list, right? So let's go ahead and return this dot size. Now you can ask the question, int n is equal to numbers dot get size, right? And only if n, like say, n is greater than or equal to 16, right? Will you ask this question here? Something like this. Right? Now it's safe. Right? But it was only safe because we gave access to the outside world a little bit of information here. You can now go ahead and ask if there are that many elements in there and look before you leap. Okay? I'll go ahead and restore this though. And let's ask for something that we do know exists, say index 5, which should be 60. There we go. Check mark. Check mark. remove things or modify things. Before we do that, let's rethink yeah, let's go ahead and remove things. No. Let's go back to add things here. So all we have right now is add element to the end of the list. Can you think of another useful piece of functionality that you might want if you were shopping for your own list? What if there was 10, 10, 20, 30, 40, 50 elements in there? Should you always just add it to the end? Where else might you want to add? Middle? Like right there? Right. Beginning? Right there? Let's take care of all of them. You can add it to an arbitrary index. Right? So think about this in terms of indices. 0, 1, 2, 3, 4. Right? And then 5, which is empty. Okay? If you wanted to add, say, 42 at index -1, and this is our item, what does that mean? That means that you're adding it right here? That doesn't sound right. So this is error. Right. Result. What if you wanted to add 42 at index 0? That kind of makes sense now, because you're saying that you want to put it here. Should we get rid of 10 though? Probably not. Let's take all of this stuff, shift it down so that it's 10, 20, 30, 40, and 50 now, so that we can make room to put in 0 right there, or 42 right there. Right? So shift stuff down from index 0, and that makes room for it. What if you wanted to insert it at 1? That means that, would you shift everything down now? Nope, you'd only take this stuff and shift it down. So in other words, shift everything down from I equals 1. Right? Dot, dot, dot. You can imagine what this looks like. So the size here is going to be 5. Right? So when we get up to, say, 4, we're going to shift everything down from I equals 4. In other words, we're going to take this guy and move him over here so that we can put 42 right here. Okay? Does it make sense, though, to say that you can add it at index 5? Sure. What would that look like? There's 42. Do I need to shift anything down? No. Gee, that looks familiar. Do we already have that functionality? Yeah. What is that? Add it to the end. Right. So let's think about how to implement this. We're probably not going to get it done today, but we'll go ahead and pick it up there on Friday. Let's at least write a part of the function. Public void add element. Can I call it the same thing? Nope.
Add element at index.
All right, at index. And so I'll also give you an index. There we go. All right. So my first step is shift stuff down from index up to the end. Right. Okay. Let's come over here and visualize this. So let me grab all this. Come on, copy. And paste. There we go. All right, so I need to shift everything down. Say that I'm going to insert it right here. I'm going to start at 3. So can I take 40 and simply just copy it over here to 50? What happened to 50?
It's gone now.
It's gone. Right? Likewise, if I started over here, can I take 10 and just copy it over here? What happened to that 20? Gone. Right? So do I really want to work left to right? Probably not. What if instead I worked right to left? I took 50 over here and I moved it over here. Right? And then that frees up this one so that I can take 40 and move it over here. Right? That frees up, then that's where I'm done, because this is where I actually want to insert it. Right? So let's start from the right and work left. Yeah, go ahead.
Error case because of that plus 10 that you had. If the array is full, there's no annotation.
We'll take care of that on Friday. Right? So what I'm going to do is I'm going to start from the end and work up to index. Dot, dot, dot. Copy array sub I into array sub I plus 1. Right. Now let's write that loop as our last exercise for the day. For int I equals, where do I start now? At the end. Where's the end? This dot size, if there are 5 things in there, 0, 1, 2, 3, 4, I want to copy 4 over here, so it would be size minus 1. Then I would then I would go up to or down to or up to, I don't know, you tell me. I'm going to copy array sub I into I plus 1. There we go. So where do I go up to, where do I go down to? If I'm working left to right, I'm now working down. Right? So where do I go down to? Well, I is greater than or equal to, all I'm doing is taking this from index up to the end, and then I'm just simply reversing it from the end down to index. Now should I go I plus plus? That's going in the wrong direction. If I'm working left to right, what do I do? Minus, minus. There we go. That will certainly shift stuff down. Let me go ahead and try this. Numbers dot add element at index. Let's go ahead and add 101 to index 4. 0, 1, 2, 3, 4. So I'm going to shift everything down here to the right. And let's go ahead and see if it works. Obviously it's not done yet, but is my shifting working? There, 50 was copied over, 60 was copied over, 70, 80, 90, 100. We lost 42 though, why? Well, because we're not done, right? Once I've shifted everything over, I also didn't get 101 into there. So what do? This dot array sub index, oops, oh, home row, is equal to x. What else do I need to do? If you're adding something to a list, it grows, right? If it was 5 things before and you added in something else new now, it doesn't matter where you added it. How big is it now? 6. So this dot size plus plus. Let's see if that works. There we go. 101 is now right in the middle, and I didn't lose anything. Everything was automatically shifted down. We'll pick it up here with some corner cases on Friday, but what I want you to start thinking about in the back of your mind is, ooh, what if I always add something at the beginning? I've got 10 things that I need to shift down. That's 10 operations. What if the list was of size 1 million, and you're always adding to the front here? 1 million things needs to be shifted. 1 million things needs to be shifted. 1 million things needs to be shifted. Plus 1, plus 1, plus 1 each time. Does that sound efficient to you? Probably not. So this is why if you use one list, everything is good to go. If you use a different list for the exact same application, now it's going to take months to execute. Right? That subtle little difference there makes the difference between a programmer and a computer scientist, knowing the difference. Right? All right, we'll pick it up there on Friday.